All right, friends, it's already been 3 years since we first saw those groundbreaking scientific images from the flagship space observatory. Since then, the number of photos has only grown, and with them, a wave of discoveries that keep reshaping our understanding of the dawn of the universe. This past year, we've continued to be amazed by spiral galaxies in the early cosmos, received fresh data on supermassive black holes, the evolution of our solar system, discovered a brand new moon of Uranus, and even had a brief scare from an asteroid that luckily will just pass us by. But in this first part of our 2-episode review, I want to start with exoplanets, the ones that astronomers managed to capture directly, planets spiraling into their stars, and even free-floating worlds that might host their own systems. We'll also talk about young stellar systems where water ice was detected for the first time, the mystery of star formation in the core of the Milky Way, and finally, a new planet candidate in the legendary Alpha Centauri system. Now, when we talk about direct imaging of exoplanets, it may sound like just a neat way to get a spectacular picture, a kind of technological showcase, proving that astronomers can actually snap photos of alien worlds. But this method is far more important than it might seem. Here's why. When you see a planet separately from its star, you can measure its atmospheric chemistry with incredible precision, without the interference of starlight. That's a huge advantage for anyone studying distant worlds. And the light you're seeing isn't only starlight reflected off the planet's atmosphere or surface, it can also be the planet's own thermal emission. That's especially fascinating, because in the infrared range, planets shine relatively brighter compared to their stars than they do in visible light. That's why young planets still glowing from the heat of their formation, as well as gas giants that retain internal warmth for billions of years, are perfect candidates for direct observation. Plus, infrared spectra reveal molecules that are tough to detect in visible light, things like carbon dioxide, methane, or water vapor. Of course, direct imaging is incredibly challenging, and in most cases, nearly impossible. Planets are far too small compared to their stars, and thousands or even millions of times dimmer, which makes them vanish in the glare. And if you think James Webb is the ultimate tool for this, well, not exactly. Its mirror is smaller than that of some ground-based observatories, and soon it'll be outperformed in resolution by giants like the Giant Magellan Telescope or the Extremely Large Telescope. But Webb does have one crucial advantage. Earth's atmosphere blocks a huge portion of infrared light, making it invisible from the ground. Webb, on the other hand, is equipped with instruments that, for the first time, let us explore planets in the mid-infrared range. And that's its real superpower, the feature that has opened entirely new horizons for exoplanet science. For example, in March 2025, a team of astronomers presented stunning images of planets in the well-known systems HR 8799 and 51 Eridani. Now, it's worth pointing out right away, this isn't the first time astronomers have seen these worlds directly, since, as I already mentioned, we do have powerful ground-based observatories with excellent resolution. But this is definitely the first time these systems were observed at a wavelength of 4.3 microns. That's the mid-infrared range. On Earth, this wavelength is blocked by carbon dioxide in our atmosphere. And that's exactly why this compound had previously gone unnoticed in the HR 8799 system. Webb, however, revealed for the very first time that all 4 of its planets are rich in carbon dioxide. All 4 are gas giants with masses between 6 and 10 Jupiters, and such a high concentration of carbon dioxide is actually a major clue about how these worlds might have formed. The thing is, carbon dioxide indicates a significant abundance of heavy elements, things like carbon, oxygen, iron, and so on, deep inside the planets. And as it turns out, these planets are more enriched in metals than their star itself. That's only possible if the gas giants first formed around a massive rocky core, which later accreted gas from the surrounding disk. This formation model is called core accretion. In fact, Jupiter and Saturn formed in exactly this way. So, direct imaging has helped us understand the formation history of this planetary system. But perhaps the most fascinating part of these images are the colors of the planets. And of course, they're not random. This is how the planets look in the mid-infrared. You wouldn't see this kind of contrast at other wavelengths. Astronomers still can't fully explain why each planet has its specific shade. The leading idea is that it depends on the chemical composition of their atmospheres. For example, the amounts of carbon monoxide, methane, and carbon dioxide. Each of these compounds has different concentrations in the atmospheres of those planets. Another possible factor is clouds and dust particles, which determine how deep into the atmosphere Webb is actually looking. So the final images we see are directly shaped by the physical and chemical processes unfolding inside those planetary atmospheres. However, while the planets in the HR 8799 system had been imaged even before Webb, in June 2025, astronomers announced the very first planet discovered by this telescope using the direct imaging method. This world may be similar in mass to Saturn and orbits the star TWA7, about 110 light-years away. For now, it's only a candidate. Its planetary status still needs confirmation. But if astronomers succeed, it will become the lowest mass exoplanet ever observed directly. Another fascinating direct image came from the system of 14 Hercules, located just 60 light-years from us. In fact, this is a truly unique image, because the local planetary system is one of the most exotic we know. At least 2 gas giants exist here, and their orbits are tilted about 40 degrees relative to each other. In other words, these 2 planets practically trace the shape of an X with their orbital paths. Astronomers can only speculate on what forced these worlds off their original courses after formation. One leading hypothesis points to some kind of extreme gravitational disturbance, possibly caused by a third planet that was once ejected from the system. Whatever the case, the 2 surviving gas giants, each 7 and 8 times more massive than Jupiter, are now locked in a constant gravitational dance. As a result, their orbits are highly eccentric, stretched and elongated, but still considered stable for now. As for Webb's image, what we actually see here is Planet C, which lies farther out, while Planet B and the star itself were hidden by the coronagraph. This is the very first time an exoplanet has been directly imaged in a system with such unusual orbital dynamics. Thanks to this observation, astronomers were able to refine the properties of Planet C. Its orbit averages about 15 times farther from its star than Earth is from the Sun, somewhere between the distances of Saturn and Uranus in our solar system. On top of that, this world turned out to be cooler than expected. You see, astronomers can usually predict the amount of thermal energy a planet should emit based on its age and mass. But in this case, the temperature was measured at just about -3 degrees Celsius, making it the coldest exoplanet ever captured through direct imaging. Sure, it's really cool to watch planets orbiting distant stars, but what about planets that actually fall into their stars? Back in 2020, astronomers at Palomar Observatory spotted a strange optical brightening event. The survey behind this detection is called the Zwicky Transient Facility, and it specializes in catching unusual cosmic events where brightness changes rapidly, sometimes within just hours. Usually, this means things like novae, not as bright and far less powerful than the famous supernovae. A nova happens in a binary system where one of the stars is a white dwarf. As the white dwarf pulls in material from its normal companion, its gas envelope can ignite at a certain point, creating a burst of light without destroying the dwarf itself. That's a nova. Astronomers know these events well and understand how they behave. But the optical outburst spotted in 2020, designated SLRN 2020, was different. Observations from multiple ground-based telescopes showed there was no hot gas or dust in the system, unlike in typical novae. Instead, both the gas and dust were cool. So clearly, this was something else. When astronomers dug through archival data from the old NEOWISE infrared space telescope, they discovered that the system had actually brightened in the infrared about a year before the optical flash. And that turned out to be the key clue. Very few processes in the universe first brighten in infrared and only later in visible light. The conclusion? Astronomers believe this was the very first observation in history of a planet being swallowed by its own star. The thing is, astronomers had long predicted that one day they might catch such an epic event, and they modeled what signs to look for in the sky. The expectation was that a compact planet, before its final plunge, would spiral closer to its star and begin pulling out streams of hot gas. Once that gas escaped into space, it would cool and condense into dust. And it's this warm dust that should shine in the infrared, exactly what NEOWISE seems to have detected. Then, after the planet finally falls into the star, there could be a bright but short-lived burst of light in the optical range, precisely what was recorded back in 2020. It's worth noting that astronomers had already noticed chemical traces of such engulfment events in many other systems, but in those cases, they only saw the aftermath, stellar atmospheres contaminated with heavy elements. This, however, was the first time they witnessed the process of large-scale engulfment itself. So, as for what happened, astronomers have no doubt. The only mystery left is the details. Why exactly did the planet fall into its star? At first, the main idea was that the star had reached the late stages of its life, expanded into a red giant, and in doing so, engulfed its planet, which, by the way, was probably about the size of Jupiter. But according to research published in April 2025, James Webb told us a different story. Using its sensitive NIRSPEC instrument and far superior resolution, Webb was able to reveal faint emissions from the star and its immediate surroundings. It turned out the star's brightness was far too low for a red giant. In fact, its mass is about 15% less than the Sun's, and given its age, around 4 billion years, it simply couldn't have evolved off the main sequence yet. So astronomers ruled out the expansion and engulfment scenario. Instead, they proposed that the planet itself somehow drifted inward toward the star. Why it did so remains unclear. The authors suggest it could be due to tidal effects from the star, or perhaps gravitational interactions with another body. But the second option seems unlikely, since such interactions would have made the planet's orbit elliptical, and that doesn't match the collision model. In any case, thanks to James Webb, astronomers can now study the details of these extraordinary events, planets falling into their own stars, in ways never possible before. And with upcoming wide-field surveys like the Vera-Rubin Observatory, we can expect to catch more of them. The Webb-Rubin tandem looks truly promising. There's another class of astronomical phenomena that Rubin, paired with Webb, could take to a whole new level of understanding: the so-called rogue planets, freely wandering through interstellar space. Technically, such objects aren't considered exoplanets, at least not strictly. Astronomers still debate how to classify planetary mass bodies that aren't gravitationally bound to a star. But regardless of the labels, James Webb has studied one such object. And the goal wasn't just to pin down its basic physical parameters, but to actually reveal what's happening inside the atmosphere of this interstellar traveler. The target was SIMP-0136, a well-known, fast-rotating, free-floating object in the constellation Pisces. It's about 13 times more massive than Jupiter, sitting right at the boundary between planets and brown dwarfs. Located just 20 light-years from Earth, it's also one of the brightest objects of its kind in the northern sky. That makes it a perfect target for exploring weather on alien worlds. No surprise, then, that SIMP-0136 had already been studied extensively with ground-based observatories, as well as space telescopes like Hubble and Spitzer. Those earlier observations revealed variations in its brightness, a strong hint of a dynamic atmosphere with clouds. But Hubble could only probe a narrow slice of the near-infrared spectrum, while Spitzer recorded just a handful of brightness measurements. Webb, on the other hand, captured the full atmospheric dynamics in incredible detail. The team used its near-infrared spectrograph to record thousands of individual spectra. In fact, the instrument was taking spectra every 2 seconds, over more than 3 hours, essentially covering one full rotation of the object. Then, with Webb's mid-infrared instrument, they repeated the process. Hundreds of spectra every 19.2 seconds, during another full rotation. Crucially, each instrument captured data at different wavelengths, which means astronomers could literally see how the spectrum of this interstellar planet changed over time. The result? Hundreds of detailed light curves, each tracking brightness at different wavelengths. On this diagram, for example, you can see what was happening in SIMP-0136's atmosphere on July 23, 2023. The red curve shows brightness at wavelengths between 0.9 and 1.4 microns. That light comes from deep layers of the atmosphere at pressures around 10 bars, about 10 times Earth's atmospheric pressure at sea level. Researchers suggest that clouds of iron particles may form here. The yellow curve, covering 1.4 to 2.4 microns, traces brightness from layers at about 1 bar of pressure, meaning higher up in the atmosphere, where the clouds are made of tiny grains of silicate minerals. The variations here reflect patchiness in the cloud cover, brighter and darker regions across the planet. Finally, the blue curve shows light from the very highest layers, above the cloud decks, at pressures below 0.1 bar. Brightness changes here are linked to temperature variations as the object rotates. Hotter, brighter spots could be tied to auroras, which, interestingly, had already been detected on SIMP 0136 at radio wavelengths. Or they could simply be deeper, hotter gas pockets rising and cooling near the surface. Some of the light curves didn't match clouds or temperature changes at all. Instead, they pointed to variations in atmospheric chemistry, specifically differences in carbon abundance. So from the simple fact that the object's brightness varies with time, astronomers were able to move all the way to understanding how its atmospheric layers evolve in real time. A significant leap forward for both exoplanet science and the study of rogue planets. By the way, when it comes to rogue planets, there's another fascinating question that puzzles astronomers. Could such objects host their own satellite systems, or should we even call them miniature planetary systems? On July 30th, 2025, a team of astronomers published a study where, using James Webb, they observed 8 free-floating worlds with masses between 5 and 10 Jupiters. So in this case, we're clearly talking about planetary mass objects, not brown dwarfs. The results were striking. 6 of them showed excess emission in the mid-infrared range, a clear signature of warm dust disks surrounding them. Could it be that even these lonely worlds are capable of forming their own planetary systems? Perhaps the strongest evidence comes from Webb's detection of silicate grain emission within those disks, along with signs of grain growth and crystallization. The shape of the silicate emission lines in the spectra tells astronomers about grain size, and what they saw was unmistakable. The grains are growing. This is a critical clue because crystalline silicates are tough. They can survive the turbulent environment of a dust disk and allow clumps of material to form. Over time, such clumps can grow into planetesimals and potentially into planets, mini-planets, or moons. Interestingly, the same team had already studied other planetary mass objects and found that their disks can persist for several million years, which means these free-floating worlds genuinely have the potential to build miniature planetary systems of their own. The authors note that such systems would resemble our solar system, but scaled down by a factor of about 100, both in size and mass. Whether compact, free-floating planetary systems truly exist remains to be confirmed through future observations, but the possibility itself is nothing short of intriguing. Without a doubt, one of the most exciting discoveries in planetary science came literally a day before I started working on this episode. On August 7th, 2025, it was announced that James Webb had, for the first time, directly imaged a planet in the legendary Alpha Centauri system. It's no secret that Alpha Centauri is the closest stellar system to the Sun. It's a triple system, Alpha Centauri A and Alpha Centauri B, both Sun-like stars, orbit each other as a pair, while Proxima Centauri circles around them on a much wider orbit. Proxima already hosts at least 2 confirmed exoplanets and 1 candidate, making it one of the most important targets in exoplanet research. But things have always been more complicated with its bigger neighbors. Back in 2012, astronomers announced a possible planet orbiting Alpha Centauri B based on ultra-precise measurements from the HARP spectrograph at ESO. It appeared to be an Earth-like world with an orbital period of just 3.2 days. However, later analyses showed this signal was nothing more than an artifact of the radial velocity data processing. Then, in 2021, a planet was tentatively reported around Alpha Centauri A using data from the Very Large Telescope. But even that discovery could not rule out the possibility of an image artifact, or perhaps a clump of zodiacal dust. Now we have a fresh attempt, this time with James Webb. In 2 new papers, astronomers announce a new candidate orbiting Alpha Centauri A. Capturing such an image is an incredibly delicate process. Even around the nearest stars, directly imaging planets is extraordinarily difficult. And in a binary system, the glare from the companion star makes the task even harder. The first observations were carried out in August 2024 using Webb's mid-infrared instrument and its coronagraph. The team successfully blocked out the light from both stars to reveal an object that is about 10,000 times fainter than its parent star, Alpha Centauri A. Based on its brightness, the object is likely a gas giant with a mass comparable to Saturn. It appears to orbit its sun-like host star on an elliptical path between 1 and 2 astronomical units away. That means, if confirmed, the planet actually lies within the habitable zone. A fun detail for fans of the movie Avatar. Pandora was imagined as a moon of a gas giant orbiting in Alpha Centauri's habitable zone. Unfortunately, this new world still has only candidate status. Follow-up observations in February and April 2025 did not detect it again. However, simulations suggest this was to be expected. In about half of the models, the planet would have been too close to its star at those times, hidden behind the coronagraph's mask. If confirmed, this would be the closest planet ever directly imaged around a sun-like star, and also the nearest exoplanet to us discovered by direct detection. Discoveries like this are especially thrilling because they concern our immediate stellar neighborhood. Barnard's star has already surprised us before, and Alpha Centauri might be next. So, we'll have to wait. And unfortunately, confirmation may not come anytime soon. Well, finally, the #1 discovery in planetary science over the past year still belongs to K2-18b. The news that traces of life were allegedly detected in the atmosphere of an exoplanet spread across the world, of course with a fair share of exaggeration, as often happens. In reality, there are still many open questions, both about the detection itself and about whether dimethyl sulfide should even be considered a true biomarker. I already made a separate video on this topic, so I'll just refer you to it if you want all the details. For now, let me just add that a number of scientific papers have since been published, showing that this discovery was declared far too hastily. The supposed detections of those molecules may very well be false positives. Still, regardless of how this story ends, it's amazing that James Webb is now beginning to open up not only the atmospheres of gas giants, but also those of smaller worlds to detailed study. Perhaps someday a truly Earth-sized planet with a relatively thin atmosphere will reveal its chemical secrets to us. But for now, 3 years into the observatory's mission, we're still waiting for that moment. Water is one of the most common compounds in the universe, a substance essential for life as we know it, and therefore one of the most sought-after targets in exoplanetary science. But astronomers are not only interested in its liquid form or vapor, which are found almost everywhere. They are especially interested in water ice. In young stellar systems, giant planets are thought to form beyond what is called the snow line, the distance from a star where the protoplanetary disk can sustain water ice. Crystals of ice help material clump together into large, slushy bodies that may eventually become the cores of giant planets. These cores can then accrete gas, building the bloated atmospheres of worlds like Jupiter and Saturn. For terrestrial planets, the role of water ice is even more crucial. At least some of Earth's water may have been delivered by asteroids and comets formed beyond the snow line, later drifting inward due to gravitational interactions. That's why observing these processes in other stellar systems is key to understanding how our own solar system evolved. And yet, despite infrared telescopes revealing many dusty young systems, such as Vega and Fomalhaut, astronomers had never directly seen water ice in any of them. That changed in May 2025, when a team using James Webb reported the first reliable detection. They used Webb's near-infrared spectrograph to study the debris disk around HD 181327, a star slightly more massive and hotter than the Sun, located 155.6 light-years away, and only about 23 million years old. The system had been studied before. Here, for instance, is an image of its disk taken with the Hubble Space Telescope. The disk lies about 86 astronomical units from the star, even farther out than the Kuiper belt in our solar system, which makes the comparison very natural. In the spectrum, Webb detected distinct peaks around a wavelength of 3 microns. This feature, known as the Fresnel peak, is caused by light scattering through tiny ice grains just a few millimeters across. These crystals are mixed with dust, forming something like dirty snowflakes, exactly what one would expect in a debris disk. Webb also found that the distribution of water ice is uneven. In the outer regions of the disk, the concentration reaches about 20% relative to other material, while in the middle region, it drops to only around 8%. Closer to the star, almost no ice is seen, likely because stellar radiation has destroyed it, or because local planetesimals have already absorbed it into their interiors. This is a truly exciting result, a brand new step in exploring young stellar systems. These first detailed measurements of water ice distribution provide key clues to the processes that shaped our own solar system at its dawn. One of the most fascinating regions in our galaxy is its very center. As you know, this is where a supermassive black hole sits, feeding on surrounding matter. But it's not just the black hole. There are also countless stars and vast clouds of interstellar gas and dust. And yet, one long-standing mystery remains: star formation. With so much dense gas and dust present, why are so few stars being born here? Based on the amount of molecular gas in the galactic center, the rate of star formation is about 10 times lower than expected. Now, thanks to James Webb, astronomers have a new clue. What you're looking at is a stellar nursery known as Sagittarius C. Without a doubt, it's one of the most extreme star-forming regions in the Milky Way, lying just 200 light-years away from the famous black hole Sagittarius A star. In 2023, a team of scientists used Webb's infrared vision to peer through thick clouds of gas and dust in search of newborn stars. And indeed, beyond the sheer beauty of this image, they spotted a number of protostars. But that wasn't the only discovery. Unexpectedly, they also found dozens of bright, thread-like filaments of plasma spiraling across the region. The researchers suspect that these filaments hold the key to understanding why star formation is so suppressed. Their idea is that the filaments are shaped by powerful magnetic fields stretching outward from the supermassive black hole. These fields are generated by the swirling motion of hot plasma around it. The magnetic pressure is so intense that it literally counteracts gravity, preventing the gas clouds from collapsing into stars. So, instead of collapsing, the material twists into dense filaments, precisely what Webb has now revealed. This is the first time astronomers have directly observed magnetic fields suppressing star formation even on relatively small scales. This is the globular cluster M4, located about 5,600 light-years away in the constellation of Scorpius. Its stars are among the oldest in our galaxy. Like most such clusters, they are extremely poor in metals, that is, in heavy elements. This makes sense since they formed in the early universe, at a time when very few of these elements even existed. For a long time, astronomers believed that in such metal-poor environments, planets simply couldn't form. But in 2003, Hubble showed otherwise. In the core of M4, astronomers discovered a giant planet orbiting a strange pair, a pulsar and a white dwarf. That planet turned out to be the oldest ever found. So how did it get there? This suggested that even in regions poor in heavy elements, planets can still grow to the size of Jupiter. The real challenge, however, is time. Young stars evolve quickly. After their protostar phase, they reach the main sequence and begin emitting intense radiation that blows away the surrounding gas and dust. In theory, in low metallicity environments where there is less dust, this process should be even faster, because dust can act as a kind of protective shield for the disk. Without enough dust, disks might only survive for 1 to 3 million years, far too short for a gas giant to form. Indeed, between 2009 and 2010, observations revealed a lack of disks around stars in such environments. But then Hubble changed the picture again. In the Magellanic Clouds, astronomers found hundreds of young stars with disks, many of which survived for more than 15 million years. To finally resolve this puzzle, a team of scientists turned to James Webb. They once again observed the small Magellanic Cloud, focusing on its massive star cluster NGC 346, the same region where Hubble had found those candidate stars with disks. This time, Webb not only confirmed the disks photometrically, but also spectroscopically. And even more striking, Webb detected ongoing accretion, proof that stars were still actively feeding from their disks, even at ages of 20 million years and beyond. The result is clear. Even in metal-poor environments, planets have plenty of time to form, which means that we can and should search for them everywhere, even in ancient stellar populations like globular clusters. And once again, this shows us how our understanding of the universe keeps changing, especially when powerful new instruments reveal fresh details. And it's not just about planets. The same is true on much larger scales for galaxies themselves. Over the past year, James Webb hasn't so much simplified our view of early galaxies as made it even more puzzling. Instead of just tiny, primitive structures, Webb keeps showing us well-formed disk galaxies, some remarkably similar to the Milky Way, appearing at times when, by all accounts, they shouldn't even exist. But that's a story for the next chapter, where we'll also look at some equally stunning discoveries about black holes. So stay tuned.